Machine learning models or language models do not consume textual data as an input. Therefore, this textual data gets converted into numerical format called tokens. Once this textual data is converted into tokens, various embedding techniques are applied which facilitates these models to learn the patterns from these tokens to understand the human language. In this video, we are going to talk about the embedding concepts and different embedding techniques.
First thing first, let us try to understand how text data is converted in number format for ML models. In the realm of natural language processing, recognizing that machine learning algorithm operates with numerical input is essential. Thus, text data must undergo a transformation into a numerical format for these algorithms to comprehend and manipulate. Consider this as our sample text data corpus. This corpus being small requires minimal normalization or cleanup because this is already in a good shape. For simplicity, we will convert it to lowercase. Following this, we perform sentence segmentation, breaking down the corpus into individual sentences. Subsequently, tokenization is applied, treating each word as a token. Each unique word receives a distinct numerical identifier like this. Using these tokens, sequencing creates the vector representation of each sentences. Finally, the padding ensures a uniform sequence length by adding zeros at the beginning. The addition of padding not only ensures uniformity in the sequence length but also plays a pivotal role in optimizing matrix manipulation, enhancing the overall efficiency of a numerical operation in natural language processing. Padding can be done even towards the end of the sequence. Traditionally, words are treated as atomic unit or tokens, with each unique word or subword in the corpus assigned a distinct numerical identifier. Following the preprocessing, our corpus has undergone a transformation into numerical representations through encoding and tokenization, where each word is uniquely assigned a unique number. For instance, cat might be represented as number 3 and dog as number 2. Our current methodology treats word merely as atomic units, termed tokens, assigning each unique word or subword a distinct number within the corpus. In mathematics or in statistics, a vector is an ordered set of numbers that represents a point in space, denoting both magnitude and direction. In the context of learning contextual relationship between words or tokens, vectors are very powerful, and that is why they are used. Now, for our given corpus and converted tokens, when visualizing this representation in an n-dimensional vector space, a linear arrangement is observed. Each word is situated at a specific distance from a reference point with their orientations or directions uniformly aligned, erroneously suggesting that each word in this corpus sharing common meaning. This linear alignment stems from machine learning models lacking an understanding of the broader context of human language. For instance, the model needs to discern the similarities between cat and dog, such as both being pet animals with common features like 4 legs and 2 eyes. Simultaneously, the model should recognize distinctions like contextual differences between animal and home. Beyond this basic mapping of words to numbers or to one-dimensional vectors, our current approach lacks additional contextual or semantic information. So how to fix this? One-dimensional vector representations inadequately capture the nuanced relationships between words in our corpus. It is evident that one-dimensional representation is insufficient, prompting the need to transition to multi-dimensional vectors for a more detailed understanding of relationships. This transition involves representing words in a multi-dimensional space using floating point numbers. The use of floating point precision introduces additional intricacies in both vector magnitude and direction, enhancing the establishment of nuanced and detailed relationships between these points. This facilitates a more granular understanding of contextual relationships. So, if we do that, our word and sentences will transform into multi-dimensional vector representation like this. This is what we call embedding. Okay, so what is embedding? In the simplest form, we can say that an embedding is a vector list of floating point numbers. An embedding attempts to map data tokens to a low dimensional space where similar tokens are mapped to vectors that are close to one another by some metric in the embedding space, like cosine similarities. Embedding captures the meaning, similarities, relationships, and the context between words and sentences based on their placement in the text corpus. The distance or the angle between two vectors measures their relatedness. Embeddings are the backbone of almost all NLP tasks like search, clustering, recommendation systems, anomaly detection, question answering system, classifications, and many more. Most common embedding includes word embedding. Word embedding represents individual words as vector. These vectors are typically learned from a large corpus of text, and they can be used to capture the meaning of words and their relationships to other words. Sentence embeddings. Sentence embeddings represents entire sentences as vectors. These vectors are typically created by averaging the word embeddings of the words in the sentences, and they can be used to capture the meaning of sentences and their relationships to other sentences. And then the document embedding. Document embeddings represents entire document as vectors. These vectors are typically created by averaging the sentence embeddings of the sentences in the document, and they can be used to capture the meaning of the documents and the relationships to other documents. In statistics, there are several measures and methods to quantify the similarity between two vectors in a vector space. The choice of similarity measure depends on the nature of the data and the specific requirements of the analysis. Each measure has its strengths and weaknesses, and it is important to choose the one that aligns with the characteristics of the vector being compared and the goals of the analysis. Using a similarity measure like cosine similarity or Manhattan or equivalent distance, semantically similar sentences can be found. Cosine similarity is commonly used in text data mining, information retrieval, and recommendation system. Unlike distance metrics, cosine similarity measures the cosine of the angle between two vectors other than their distance. Because this similarity measures uses of cosine of the angle between vectors, the magnitude is not a matter of concern. This feature is really helpful for text vectors that can often be really long. Instead, the output of cosine similarity yields a value between 0 and 1. Let us plot our word embedding vector into n-dimensional vector space and try to develop some intuition about its working. We can see that the angle from 0, 0 between cat and dog is smaller than cat and home. Therefore, using this representation and cosine similarity measure, machine learning models will be able to deduce the relationships between cat, dog, and home. Now we know something about word embedding. Let us see how same concept is extended to sentence embedding. This is our sample text corpus. By representing sentences from our sample text corpus in a multi-dimensional vector space using the average of word embeddings, machine learning models can discern relationships at the sentence level. For instance, considering a question answering system using this sentence embedding, somebody asks a question like, is cat a pet animal? Initially, we convert this question in a similar n-dimensional vector form using the same model applied to our text corpus. Subsequently, we plot this question vector in the same n-dimensional vector space. Finally, we apply cosine similarity between question vector and all available sentence vector in that vector space. Observing the vector space, the angle between is cat a pet animal and cat is a pet animal is notably smaller compared to other sentences. Therefore, this sentence, cat is a pet animal, is the best matched context to answer this question. So this is how the sentence embedding is utilized in question answering system. Great. So now we develop some good intuition about word embedding and sentence embedding so far. On the similar line of word embedding and sentence embedding, document embedding can also be performed. Document embedding represents entire document as vectors. These vectors are typically created by averaging the sentence embeddings of the sentences in the document, and they can be used to capture the meanings of documents and their relationships to other documents. The documents are initially segmented into small chunks, then each chunk is embedded. Let us plot them into n-dimensional vector space, and then for any such query, first the query also gets embedded and plotted in the same vector space with same dimension. Then using cosine similarity, best match chunk or chunks are retrieved. We can see that for this search query, chunk 2 and chunk 5 are the best match, and hence they will be pulled as the final result. So this is how the document embedding is done and the use of document embedding in semantic search is performed.